So now we're going to switch a little bit and go a little bit more deeply into the technology. And I'm really excited of having Professor James Marshall here, who is not only a professor at University of Sheffield in the UK, but is also the CSO and co-founder of Opteran. And he's going to talk about a different approach to creating autonomy based on a holistic understanding of the brain. And so I think, as Steve mentioned, they've got an 8-year head start. They've developed a solution to figure out how to navigate through a warehouse based on a technology that was available at the time. Technology has changed, and we're really excited to hear what James is going to talk about the ways that they're looking at how to do autonomy on a smaller based system, right? All right.
Thanks very much. Thank you very much, and thanks, Steve, as well. So yeah, I'm going to talk about what we're doing at Opteran. So we're 4 years old, so we're playing catch up, but we're actually going really fast, I think. We're a deep tech spin out, and I'm going to explain a little bit about what we do, the science behind our approach. It's a very different approach to solving machine autonomy. And then I'm going to hand over to Jack, our commercial director, who's going to tell you a little bit about the technology, and we have a demo. I know we may be running a little bit behind schedule. I hope you're able to stick around, because we have a live demo in the room, which Chen will be happy to talk you through, and Jack as well at the end. So I'm going to talk about how to build a mind. And really it was Alan Turing who pretty much initiated the field of artificial intelligence by asking the question, can machines think, back in 1950. And this is his famous Mind article. It's well worth a read if you haven't come across it before. It's so far ahead of its time, not just in AI, but in many other areas of science. Really groundbreaking stuff, of course. Now, and his proposal was to look at the human mind and try and simulate it effectively. That was how he thought we might get towards machines thinking. In his day, it was really symbolic reasoning. That's how AI worked, or how AI was proposed to work. Nowadays, as we know, it's predominantly non-symbolic. It's quite a different approach. But still, 75 years later, and even with the recent amazing technological progression we're seeing, where's my droid? We've just seen a great talk from Steve on the kind of limitations of current approaches to machine autonomy. And I think we'll agree that what we see is a long way from, the kind of robot future that we've seen in places like Star Wars, where these machines are fully independent, human-level autonomous agents, able to just deal with adversity, able to deal with people doing stupid stuff to the warehouse, and in the Star Wars case, typically actually help the humans out and help them overcome the situations they get themselves into. Why is that? Why have we not managed that? Well, as I said, we're not really doing symbolic AI now, we're doing machine learning. And this is a nice quote from the CEO of Starsky Robotics, the first autonomous truck company. And this was from his post-mortem article on Medium, where he was saying what went wrong for them when they folded. And he said, supervised machine learning doesn't live up to the hype. It isn't C-3PO, it's sophisticated pattern matching. In other words, it's not true intelligence, and you need true intelligence for autonomy. And never mind Star Wars droids. Where's my AV or my AMR that has human-level autonomy in that more restricted domain that a driverless car or a autonomous mobile robot in a warehouse is trying to undertake? For information, so in 2022, the total spend on driverless cars, the total private spend on driverless cars development was 75 billion, according to Bloomberg. If you look at the total spend on the entire Apollo program, inflation adjusted, you have 260 billion. So in other words, we spent a quarter of a genuine moonshot program trying to get machines to do something that a teenager can learn to do effectively in a year. Why is that? Where are we going wrong? Well, to understand where we're going wrong, we have to look at how current approaches actually work. And really ask, actually, do they capture what's going on in the brain and in the mind? Are they true to Turing's original vision? If we start with the supervised machine learning, the deep learning model, deep learning is often referred to as bio-inspired, but it's actually based primarily on a pretty old understanding of a very small part of the brain, namely your visual cortex. In fact, it's not even a good model of the visual cortex when you look at how that brain region truly works, but also the visual cortex isn't the only thing you have in your head. In particular, although you use it in driving a car, you use an awful lot of other brain structures which are highly specialized in order to achieve that goal of, of driving around safely, navigating and not hitting things. If you were to try and do the job solely using your visual cortex, you'd probably be as bad as driverless cars are, which are still not human competitive. So there's something else going on that's missing in our current technology that we haven't yet captured on how brains really work. Well, maybe it's spikes, okay? Probably a lot of people now are aware that actually spikes are thought to be important. Yeah, neurons communicate with each other by sending short signals, and people like Intel have been getting into neuromorphic computing with their Loihi 2 processor, and there are many other kind of flavors available, so perhaps that's the solution. Well, actually, no, that's not the case. In fact, spikes are probably more to do with the fact that the algorithms of the brain run on wetware, so run using neurons, and more to do with the energy efficiency of how the brain actually does information processing than they are to do with the computation itself. And although there are some payoffs for efficiency of deploying AI algorithms in devices, it's not really a kind of game-changing advance in terms of the functionality and the capability of the algorithms themselves. So I've been talking about AI mainly, but another part of the puzzle is obviously also navigation, and SLAM is our predominant technology today, simultaneous localization and mapping. Is that a good model of the brain? So as you're probably familiar, it's point cloud based, so whether it's LiDAR or visual SLAM, metric mapping in 2 or 3D, and then using that for localization. And as we know, it's sensor and data intensive. We heard about networks being necessary in warehouse environments, for example. That's because the map sizes are typically gigantic, and typically for larger environments, in fact, have to be streamed in because they're too large to sit in the robot's memory. Compute heavy. The bill of materials for a mobile robot is very high. Network dependent, I just spoke about. Fundamentally, this is not how your brain works. Your brain does not represent space in this way. If it did, you wouldn't be able to remember all the places that you encounter on a day-to-day basis because it's simply too data intensive. All right, so I've told you how the brain doesn't work. How does it work? So this is, at Opteran, this is our mission, is to really understand this and see what technology we can derive from this. And we start with the observation that in fact brains evolved to solve movement, or to put it another way, move first, think later. And you might be wondering what this is. This is a tunicate, or colloquially a sea squirt. And this animal beautifully illustrates the principle that brains evolved to solve movement primarily because it has 2 life stages. It has a mobile stage during which it uses a brain, and then it has what we call a sessile phase, a non-motion phase, where it anchors itself down somewhere, and at that point it digests its own brain and nervous system because it no longer needs it. The other thing to note is brains are highly structured, and I already alluded to this. And in fact, at Opteran, we're not even inspired by the human brain or even primate or vertebrate brains. We actually look at the brains of invertebrates, insects, for example. So what you can see here is an animation of some of the beautiful structure inside the brain of a fruit fly, which has only 100,000 neurons, but can do visual navigation. My own research came out of looking at honeybees and ants, which have slightly larger brains, but still fewer than 1 million neurons. And this beautiful structure here is the ellipsoid body in the fruit fly central complex, which is fundamentally where its navigation circuits live. So with fewer than 100,000 neurons, the fruit fly is able to solve the navigation problem tremendously efficiently. And in fact, we can interrogate how the brains work to realize that brains are not only highly structured, they represent information very intelligently, very efficiently. So this is actually experiments from HHMI Genelia on the visual compass, the ellipsoid body of the fruit fly. So here you can see the fly in the experiments. It's on a virtual reality trackball, and it's controlling the environment, this virtual reality environment. So it's able to turn according to the visual input, and it's in closed loop, so as it turns on the trackball, the environment responds appropriately. At the top, you can see recordings from this ellipsoid body, and what the researchers... Okay, I can see... Yeah, okay, sorry about that. What the researchers discovered is actually that the fruit fly has a visual compass that encodes its heading in a way we can naturally read off. So you can see the green fluorescence there, that's actually a read off of the real-time neural activity in the fly's brain. that shows how its heading is changing, how its estimated heading is changing as it's controlling its heading in the environment using the trackball. And that's just a very simple example. That's like one of the simplest visual circuits. So we have this great wealth of information, really a kind of goldmine of algorithms that brains deploy to solve the autonomy problem. And at Opteran, what we do is reverse engineer insect brains to actually extract these algorithms and not to reproduce them, with spiking neural models and all of this kind of stuff, but actually figure out the information processing principles and deploy that in standard off-the-shelf technology that we have available to us today, providing the software mind that enables natural autonomy for machines. So this is the Opteran mind, and I'm just going to take you through some of the highlights, but it starts very much with low-level sensory processing and solving motion, which is visual navigation. And you can see we have low-level vision and perception algorithms feeding into action and feeding into what we call a number of cognitive engines. But what I'm going to show you first of all is at the very start of everything, what we do is what every brain does, your brain included, but also insect brains. On the right-hand side, you can see a honeybee flying around inspecting a flower, and if you look closely, you'll see actually the head is stabilized by the neck muscles of the insect. So the body effectively moves around in order to preserve a stable, rotationally free view of the world for the sensory system to perceive. And on the left, you can see one of our engineers doing exactly the same thing with one of our development kits. So this is our system. Everything is on here, and I'll explain a little bit about the hardware and the sensing side of things later. We can discuss that during the demo as well. But this is the whole thing, sensing plus compute in a very lightweight, cheap, low-energy package. And Cara, our engineer, is now doing effectively what I'm doing now. She is rotating freely the development kit, and what you can see is that actually there's a completely stable view. And then we achieve that electronically rather than mechanically, but the purpose is the same, because that simplifies downstream processing for the navigation algorithms. We call that Opteran vision. It feeds into Opteran perception, which is extracting meaningful information from your sensor feed. And here you can see one component of our VIO solution, which feeds into then things like collision prediction, et cetera, as well. And this is reverse engineered from the honeybee visual system, and what you see is it's tremendously robust. We actually have a couple of orders of magnitude, several orders of magnitude difference in light levels due to deploying this technology at dawn and then in the middle of the day. But you can see on the right-hand side, the captured information is exceptionally stable to these differences in lighting. And we call this Opteran perception. It then feeds into Opteran action along with other technologies we have. And what I'm showing here is in fact another part of our solution, which is panoramic electronically stabilized stereo vision. So this is a full 360-degree visual system, electronically stabilized, as I said. From that, we can actually do stereo estimation as well. So you'll see at the bottom, these are the raw feeds, and then at the top we'll be doing a 3D visualization of my co-founder Alex just messing around in the office. And so the panning in the top view is in fact just, we're not moving the camera system, we're just moving around where we're looking inside this panoramic view. And you can see we're doing the 3D depth, and I'll happily show you these videos again afterwards. Then all of this feeds into the first of what we call cognitive engines, which sit on top of the low-level visual sensory processing and actually generate meaningful and useful behavior. Because just like brains solve movement first, if we can solve movement first in our general progression of technology, that's already a useful technology to deploy. So we call this Opteran spatial engine, and I'm just going to let the images speak for themselves, and there will be some music, so I won't talk over that. But please give me 1 minute of your time to watch this video. So what you may not appreciate from that is just how lightweight everything is on this. So this compute package, for example, is a couple of $100, 20-year-old CMOS technology cameras running on a few watts, solving all of those problems, which are pretty challenging for traditional SLAM algorithms, and we'll show you something even more challenging at the end. And it's the first of our cognitive engines. But we have a general journey to solve machine autonomy in the round. So where are we going next? Well, we want to build out more of these cognitive engines. Having solved movement, we're then bringing in decision making in the next 12 to 18 months. So on board, fully autonomous decision making without reinforcement learning or rule-based systems to make your robot deployable in the same way that a human can be deployed on a task, that you specify the task simply through a number of priorities, and then the decision engine, the decision-making component dynamically prioritizes on the job. But then looking at social interactions, insects like honeybees are social. So I've been doing a lot of research myself on how they function collectively. And if we can decentralize the decision-making processes, traffic management and so forth, we can get away, we can increasingly reduce or eliminate entirely the need for the network in an AMR warehouse, for example. We can simplify fleet management in the way that humans working in that same environment would do so, in a completely decentralized and distributed way. And then going beyond that, reasoning about the world in terms of causation and abstraction and so forth in a very efficient manner. But having given you the kind of scientific genesis of what Opteran is doing and laid out the journey, I'd like to hand over now to Jack Pearson, our commercial director, who will just talk a little bit about how you can use this stuff now.
That's okay, I don't deserve any clapping. So, yeah, James deserves that. So James has talked to us about the amazing research, the science, the philosophy behind this new approach to autonomy. As James said, I'm here to tell you about how we've productized it, and productized it to solve one of the biggest problems in autonomy generally. So last week, I spoke to a CEO of an AMR company, and he put it really, really well. Localization technologies, autonomous localization, still fails in very, very standard warehouse environments. To counter this, often have to use infrastructure, QR codes, magnetic lines, which brings a whole host of other challenges. So really the challenges can be broken down into two areas. So if you're looking at traditional SLAM, visual-based or LiDAR-based, they rely on expensive sensors, 3D LiDAR we've seen. They rely on expensive fixed infrastructure. They rely on a lot of labor to set up, to manage if there are challenges. And yet, in very many situations that you see across warehouses and that Steve actually set up really nicely, they still break down, they still mislocalize. So we heard about changing environments. Very often in a warehouse you're going to have pallets moving, you're going to have product coming in and out, changing how the environment looks with its shape. It's very, very common to have corridors that look very similar, to have blinding from sunlight coming through a window, to have reflections, glass and mirrors. All of these things can cause mislocalizations, which in the end feed back into the cost structure. You either need to put in infrastructure or you need to bring someone to solve the problem. So Opteran really helps cut through that trade-off. So we provide highly robust localization using, as James said, the lowest end hardware and compute. So running off $10 cheap cameras, the edges of existing compute, you can get performance that matches and works really well as an addition to many of the standard approaches to SLAM localization. And so from today, we have an infrastructure-free mapping and localization software solution. It can work on its own, or it can also work in addition to an existing solution, as many AMR companies already have. But the really great thing about it is that you start off with mapping and localization, but as these other features are released, the ones that James mentioned, depth perception, collision avoidance, and in the end, a reverse engineered mind, all of these can be added and continuously upgraded. So you start with just localization, and in the end, you have a reverse engineered mind inside your machine, whether it's an AMR, a vehicle, or a drone. So I think we're going to stop for a few questions first from James, but in a second, we'd like to show you this in practice. So any questions?
I think we can both do the questions as well. So commercial ones for Jack. Yeah.
I love the neuroethology approach. Like the 90s are still alive. It's great. So, quick question about your competition. I'm wondering if you have any opinions or thoughts that you can share on liquid AI in Boston and the whole like liquid neural net movement, which is based on C. elegans.
Yeah. I'm going to say, so first thing, 90s, yeah, you're quite right, this is neuroethology. What has changed is the techniques we have to interpret the brain. So we now have brain atlases for invertebrates, optogenetic techniques to manipulate and record from the brains, which are creating really, really useful information that we actually synthesize to figure out what the algorithms are. So although it's an old idea, it's one whose time has come because of the availability of data, not for training algorithms, but for actually for humans to work out what the heck's going on in a brain. C. elegans, so a famous fruit fly scientist said something pretty rude about C. elegans, which I will not repeat, especially not on recording, but fundamentally, like, they've got a couple of hundred neurons, and they don't do very much. They wiggle around and they mate with each other. And I see, people have tried to use that for autonomous vehicle control and so on and so forth, and it can kind of work pretty well in a limited enough domain. But I don't think, C. elegans has nowhere near the kind of behavioral richness and navigational richness, especially of even a fruit fly, never mind a honeybee worker, which can fly about 7 miles out from the nest, find a food source, get back to the point of origin, and then even communicate at that point in space to nest mates tremendously efficiently. So, with fewer than 1 million neurons, if you can solve that visual navigation challenge so efficiently, I think, we clearly have a lot to learn there. And C. elegans, nice, very efficient, couple of hundred neurons, but nowhere near as behaviorally interesting.
When you're looking at kind of LiDAR-based technologies, you generate so much data,
Mm.
but in some cases, it's a good thing given that you have a quantifiable, foundational unit of number of points to be able to determine kind of these abstracted features such as risk and guarantees for specific detection of objects.
Mm-hmm.
Your guys' model, do you guys address that? Or do you say your guys' model doesn't require you to have an understanding of risk and kind of this idea of how many points are actually getting detected correctly?
Yeah, I think it's a very different paradigm. So
Yeah,
we don't need to... Ultimately, what do you care about if you're deploying a robot? In the real world, you care about, can it navigate the space effectively without getting lost and get to where it needs to be? A lot of the metrics that are deployed now to evaluate technologies, we actually are competitive with them or even exceed them in terms of localization accuracy and what have you. But you're probably quite bad at localization accuracy. Like if I said, could you localize within this room to a particular point you've been to within plus or minus 2 centimeters, you might do reasonably well, but that's not really what your brain evolved to do. But are you good at navigating through the world? Tremendously good. Do you do it efficiently? Tremendously efficiently. So you've got to think about what are the actual KPIs you really care about, the behavioral KPIs that truly count for the use case you're trying to deploy. And in terms of being able to navigate space, path planning, we don't need a path planning system, for example. We don't need to map out, do an occupancy map and all that kind of stuff, because your brain won't do that either. You'll have a navigational system which works tremendously efficiently, but then as you're moving around in a crowd on a street or something, you're dynamically avoiding objects in a purely reactive way. There's some anticipatory planning as well, but fundamentally you're doing it with 2 different systems.
So do you imagine these systems being cobots and working alongside people on warehouse floors? And how do you think people might react to robots maybe behaving a little unpredictably because they are kind of continuously making interesting decisions on their own?
Well, so what we're showing right now is purely navigation technology. So, we're not getting into the robot thinking for itself yet. We can do that in the future, but we believe that the decision making will feel pretty organic. But I'll just speak to human acceptance. So actually a big thing we've done for human acceptance of our technology is actually just try and make the navigation look very, very smooth. Because people have a lot more confidence that the robot's doing something sensible when it actually is just following a smoothly interpolated path, which strictly it might not need to do for the task. Like for an AMR, it might not be strictly necessary, but it's nice for people working around it and for people evaluating it for a particular use case if it actually looks like it's behaving very purposefully and predictably.
Do you need any charge sensor to avoid all the pollution avoided inside the camera?
So for today, yes. So obviously, many of us know 2D LiDAR is safety rated, very common in industry. So in many situations when there are people around, you'd still need 2D LiDAR, and our system can work with that. So you can have both the mapping and localization and the safety coming from safety rated LiDAR. We are going down the path of certification, and that's something that we're working towards. But from today, it's mapping and localization that can work with other sensors, whether it's 2D LiDAR, 3D LiDAR, depth cameras. In the future, we'll have the collision avoidance integrated as well.
Yeah, and what would be really interesting and what we'd be looking at is, can we get safety racing for our collision avoidance technology, because that can take a lot of cost out as well. If the safety LiDAR is just in there to stop bumping into things, because it's required, if we could solve that same problem more cheaply and get the regulatory approval, then that's another saving.
One question: have you guys deployed this technology on marine environments?
No.
And that reflection and stuff is a really big problem when you're on the water.
No, not marine. We're pretty hyper focused at the moment on a few key on ground use cases, but it is being deployed though. So should we head over to the demo?
All right.
Yeah, thanks very much.
Yep. So thank